Let's talk about simple harmonic motion. An approximation of it in terms of something you might see is that's roughly simple harmonic motion right there. Now, one of the reasons why it's not exactly simple harmonic motion is the fact that we are dealing with, there's a dampening process. You are losing energy as it goes, and in simple harmonic, energy is, we're dealing with just a conservative force and energy is conserved. Also, in the simple harmonic motion, the spring itself is massless. And all the mass, or we should say, all the mass is concentrated at the end. And obviously, a slinky has mass throughout. However, there is a lab where we talk about the effective mass of that, and we can calculate, bring that into it, and actually get pretty decent results. So, going to look at this particular situation right here. We're going to do a force diagram of this mass that is attached to the end of this ideal spring. I'm establishing this as its equilibrium position, so equilibrium. And so that's just its natural resting place. If I had the mass attached and I just sat it right there, it would sit, no forces acting on the mass. Because we are dealing with a nice ideal situation, there's no friction involved here at all. I then take the mass and I pull it out and I let go. At the moment, just after I let go, what are the forces acting on the mass?
Force to the left of the spring? Or is it?
Right, say the wording was off, or I misheard.
Force to the left on the spring. I was saying on the spring, but I think I mean from the spring.
On the mass.
Yeah, on the mass.
Okay. That's what you're,
Yeah.
that one. Okay. And there is a force in the other direction acting on the spring. So this would be, well, F sub S. Thank you. And
downward force due to weight. Well, that would be gravity.
Some normal
There's
force.
also normal force.
I would hope so. All right, and that's it. Hopefully you can visualize this enough to understand that it's not going to come off the table or dig into the table that, or surface, that these will balance each other out. So that's the net force right there. So this force from the spring is equal to mass times acceleration. Now we've got to be careful about dealing with the sign involved. So I said to the right was positive. The force is acting to the left, and so this would be negative K delta X, which is the force from a spring, is equal to mass times acceleration. And the negative here is just saying that if I displace the object in the positive direction, the force will be in the negative direction, or if I displace the object in the negative direction, the force will be in the positive direction. It's just the opposite. Part of the dealing with Hooke's law is that there's this restorative force. There's a force that's always trying to get it back into its natural position. Now, I went ahead and defined its equilibrium position as 0, just to simplify the notation. So this becomes negative Kx is equal to mass times acceleration. I am expecting the acceleration to be negative at this moment, but I'm going to keep this as a positive term here, knowing that A would be a negative number at the very beginning of the problem. So X is position, A is acceleration. What's the relationship between acceleration and position?
It's inverse of the acceleration is inverse of the position.
Not inverse.
So it'd be the same as position.
Not exactly.
It's just proportional.
All right, let's drop back a second. What's the relationship between acceleration and velocity?
The velocity is half, or not, well, acceleration is squared velocity, right?
Not necessarily. I'm sure I can come up with a scenario where that works, but
Acceleration determines what your velocity is, like.
The change in velocity.
in terms of what the change in velocity is, what's the actual math formula there?
Change of velocity over,
Change of
seconds? Change of time, yeah.
All right, so acceleration is the change in velocity over change in time. What is velocity in terms of position?
Change in, position over change in time.
All right, okay. So my acceleration is dependent upon my change in velocity, and my velocity is dependent upon my change in position. So there's a relationship, an additional relationship between x and a here, between my position and my acceleration. The acceleration definitely depends upon what my position is at any particular moment in time. From a graphing point of view, velocity is the slope of my position versus time graph. Acceleration is the slope of my velocity versus time graph. Just add them up.
So it's not Pythagorean, it's just like.
Right, the arithmetic's on this, you just got scalars in this, put a plus sign here. Also as opposed to geometric zones, which is very different. So acceleration dependent upon velocity, velocity dependent upon position, and there's this relationship we have to somehow resolve, so that if I take the slope of my position time graph to get velocity, and then I take the slope of that to get acceleration, they should look, one should look basically like the upside down of the other, because we got that negative sign there. So at this point, the math people come in, or the physicists come in, and they look at that and go, is there an equation that would work for this? Of course there is. So let's take a look at that. Let's start out with cosine. That's the basic cosine curve right there. Goes there to 2 pi. So if that's position versus time, what is the, what's the slope look like? What's my velocity time graph look like?
A sine wave? Or it would be the inverse.
Yeah, it
Okay.
would just look like the opposite.
Yeah.
All right, so for those who didn't quite catch why that's true, think about where the slope is 0 here. Slope 0 at the beginning, slope 0 at the middle, and slope 0 at the end. Between the beginning and the middle, it's got a negative slope. Between the middle and the end, it's got a positive slope. And this is a negative sine curve. So this is a cosine of time. This is negative sine of time. Now, if you have not had trig, you can play it with your calculator also, but, and just goes point by point. Sorry, bringing back flashbacks to my first year of teaching. I made some comment like that in class of, you know, you can just always go through and do it point by point. And then when it came time for the test, the student was doing point by point. They had plotted like 10 different points trying to figure out what the curve looked like. They ran out of time.
Is it a sine graph? Because at first in my head I didn't understand why it wouldn't be like a negative cosine graph, but it's because you can't start with negative velocity, right?
You can start with negative
But
velocity.
in this case,
This is a matter of fact, well, this will start at 0. When I let go, it very quickly becomes negative velocity until it gets to over here.
right? Okay.
Why did I start with cosine? Was that the first question?
No, that part makes sense. I just
Okay.
it didn't make sense when you moved it, like when you did the bottom one. I was like, it's a negative sine graph, but it makes sense now.
Okay. Let's take it the next step. If I have so if my velocity time graph looks like this, and that's 2 pi. So this is velocity versus time. That's supposed to be a reproduction of what I have over there. What does my acceleration time graph look like?
It would basically be a flat, no?
acceleration time?
Again, this is the slope of this one.
Right.
So let's first figure out where is it zero? Where is the slope of velocity zero?
At the x-axis?
It's at the peak of the trough.
At the peak, yeah. So there and there. From the beginning to the first zero here, slope positive or negative?
Negative.
In the next region, from here to here,
Positive.
and then from here to here,
Negative. It's just a negative cosine graph?
yep. So this would be negative sine of time, and this is negative cosine. If you kept going, there's a pattern that develops here. So if you start with cosine and do the slope, you'll get negative sine. From negative sine, you would get negative cosine. From negative cosine, you'd get positive sine. From positive sine, you'd get cosine again, and it just loops around. I have the eraser, there it is. Now, before we just go ahead and quickly plug in a sine and cosine, I'm gonna do one other thing here. So that graph over there was, this is, the position is equal to cosine of time. So position is equal to cosine of time. In terms of units, technically, there's a 1 radian per second sitting up front in front of the time. And there'd be a 1 meter sitting up front there. And so that plot, 2 pi is when it starts to repeat itself. All right, so if I did x is equal to 1 meter cosine of 2 radians per second time, or from a just more straight math point of view, cosine of 2t, how would this graph look different from that graph?
It would be constricted, like smaller, or would it be
This way?
larger?
Or this way?
Vertically.
Bigger, vertically.
All right, so let's think about that. What's the largest value of cosine here? What's the largest value of the position here?
1.
Okay. And the lowest?
-1.
Negative 1. All right, because the biggest value of cosine is 1, the lowest value is negative 1. Down here, what's the biggest value of cosine 2t?
2.
One.
Oh.
Is it still one?
Because you're not
Still one.
multiplying
Still
cosine by
one.
anything.
So this is still gonna go from 1 to negative 1.
Okay. So it's gonna stretch by a factor of 2?
So that way.
Yep.
Will it?
And like,
No, I don't know. I can't fight. I have nothing, I have
I
no
think-
ground to stand on.
I'm not entirely sure whether I remember, but it has to deal with, cosine's not like the actual x. If you're thinking about it quadratically, the x would be in the, next to t in this point. So when you, x would be t, so when you stretch a graph, it's stretched or shrunk by the factor of the coefficient next to the x in the
Okay.
quadratic.
so in the transformation, if I have a number in here, that's, the number next to the variable is gonna stretch it
Yeah,
horizontally or shrink it horizontally.
yeah,
The number up front would stretch it vertically.
yep. I just,
But, so you made the, but you were saying they would go out this way.
yeah, I just can't remember if it's closer or longer.
No, if
Longer,
it's one
sorry.
half, if it was 1/2, then it would stretch, right?
Yeah.
But it's 2, so it would get small.
Yep,
Because remember that this is equal to 1 when what's inside here is equal to 0, 2 pi, 4 pi, and so on. This will be equal to, this cosine will be equal to 1 when 2t is equal to 0, 2 pi, 4 pi, and so on. In other words, when time is 0, pi, 2 pi, and so on. It gets back to where it starts more often. So it would shrink it this way. So that was that. So this is now pi. So in half the space, it does the entire trip in half the amount of time. What does that do to the slope?
Increases it,
You wanna take a shot at how much?
Half.
by doubling it?
Yeah, by whatever number that is.
Yeah.
So we can go slightly more generic there, that if x is equal to some amplitude, just generically a, times the cosine of, I'll just use another letter here, omega t, so this is omega. Then my velocity graph would be a times whatever number's there, times the negative sine of omega t.
Wait, why does the omega brought out front to where the amplitude is at?
By the same token as with that 2t right there, when I did the slope,
Oh,
the slope doubles.
okay, gotcha.
If you've had calculus, you would look at this and go, oh, yeah, of course.
Yeah.
But if you haven't had calculus, later on you'll look at it, when you take calculus, you go, oh, yeah, of course. And so every time I go down the slope, whatever numbers I'm multiplying time by, I multiply it out front for the slope. So my acceleration would be negative a omega squared, as I multiply another omega, cosine of omega t. And just for the fun of it, the jerk, so we want to take a shot at what the jerk would be.
Is it tangent?
No. No.
It would just be sine, AW sine.
All right, so we got sine here.
Is it just a sine of omega time?
Now, you threw a W in here,
Yeah.
by the way, they're omegas, but, and you left them out completely.
Yeah.
I will say that neither of you are correct on the score.
And is it omega squared?
It is not.
Omega cubed.
Yes. Because every time you go down in slope, remember jerk is the slope of my acceleration graph, flash back on that one. You multiply times this again, so since I already have an omega squared here, when I multiply by omega, I get an omega cubed.
What did you say jerk was again? The slope of your acceleration?
Yes.
graph?
So jerk is technically faster than acceleration?
It's
Yeah.
acceleration.
Yeah.
It's the time rate of change of acceleration.
Is there anything faster than jerk?
You say faster, faster is really not an appropriate word here.
Is there anything that I wouldn't say accelerate, because
Is even
accelerates.
more dependent variable?
Yeah.
Is what you're looking for?
Like the change in jerk over the change in time equals what?
Is there anything
Oh.
higher than jerk?
You say higher than, as in slope of jerk,
Yeah.
gets you to snap,
Oh, okay.
and then
Crackle. Pop.
Yeah. That was so long ago. Oh my
Are you
God.
back?
it comes back though.
Are you being for real? Like, it
Yeah.
actually goes snap, then crackle, then pop?
Yeah, it hasn't been accepted by the international community at this point.
That's,
It is not.
Arbitrary names for variables no one uses.
wow.
I feel like I left one out.
I wanna find my notes on that day. Cause I remember taking notes and being like, what are we talking about?
All right, so anyway, back to simple harmonic motion. So this function actually will work. There's one other thing that I'm gonna add in here, because I have this thing starting, when time is equal to 0, I have it starting at the maximum value. Reality is, if I got this moving up and down, and then I hit the lab quest to sort of measure the motion, I'm not gonna hit it exactly at the peak. I'm not gonna hit it exactly at 0 either, at the equilibrium position, to make sine convenient. So to offset exactly the beginning point, the full generic equation would be a cosine omega t plus phi. This phi right here is known as a phase shift. And that basically, when you add something to the variable piece of it, that takes the graph and just shifts it left or right. Multiplying by the variable will shrink it or expand it, and then multiplying out front will make it grow or smaller. Notice this is also a one-dimensional equation here, and then I've indicated a positive direction. I've established it starts out initially in the positive. So if I were applying this generic equation to this problem right here, A would be a positive number. The phi here does absolutely nothing to the slopes other than you still just have plus phi, plus phi, plus phi, but it doesn't add anything to make it doesn't, since it shifts the graph left or right, it does not make the slope any taller or smaller. So now I'm gonna take my equation and I'm gonna plug it in to Newton's second law right here. So I have negative k times a cosine of omega t plus phi equals mass times my acceleration, which would be negative a squared omega squared cosine of omega t plus phi. So all I did is, once I have a generic equation which seems to fit the bill, plugging it in. So that's my x and that's my a. And now let's get rid of stuff. What can we get rid of?
Cosine, omega t plus phi.
All right, that goes away.
Oh, never mind. Would A? No, because it's negative. Unless,
Oh, that shouldn't be squared there.
Yeah, I was gonna say, when did we square that?
We can get rid of a couple more things. It seemed like you left off with what we could not get rid of.
well, yeah, we can't get rid of A because it's negative, but omega squared, well, where's our, yeah,
Should we change negative k to negative 1/2 mass times acceleration, and then we can cancel out mass? Cause k is.
No, we don't want to.
Okay.
I'll right here.
K is kinetic energy, right?
No, K is the spring constant.
Oh, sorry. See, I was thinking it was.
You go away for Thanksgiving.